Welcome to Science for Sleep. If you enjoy long, calm documentaries like this, you can gently subscribe now and settle in as we begin our slow descent. Heat at the ocean's surface. At the very top of the ocean, temperature behaves in a way that feels familiar to us. It rises with sunlight, cools at night, shifts with the seasons, and responds quickly to the movement of air above it. This thin surface layer, often no more than a few meters deep, is where the ocean and the atmosphere constantly exchange energy. It is the most dynamic thermal environment in the entire marine world, and it sets the stage for everything that happens below. Sunlight is the primary source of heat for Earth's oceans. Each day, solar radiation travels through space and reaches the surface of the sea, where a portion of that energy is absorbed by water molecules. Unlike land, which heats and cools rapidly, water absorbs heat more slowly, but stores it efficiently. This property allows the ocean to act as a massive thermal reservoir, smoothing out temperature extremes across the planet. Coastal regions experience milder climates because the ocean releases heat gradually, warming the air in winter and absorbing excess heat in summer. At the surface, temperature is never truly constant. Even on calm days, subtle variations appear as sunlight shifts across the sky, clouds drift overhead, and wind patterns change. In tropical regions, surface temperatures often remain warm year-round, sometimes exceeding 28 degrees Celsius. Near the equator, the sun's rays strike the ocean almost directly, delivering concentrated energy throughout the year. In contrast, toward the poles, sunlight arrives at a lower angle, spreading the same energy over a wider area and resulting in much colder surface waters. Wind plays a crucial role in shaping surface temperature. When wind moves across the ocean, it stirs the uppermost layer, mixing warm water with slightly cooler water beneath. This process prevents extreme heating at the very surface and distributes energy more evenly. Strong winds can enhance evaporation, which removes heat as water molecules escape into the air. This evaporative cooling can lower surface temperatures significantly, especially in dry or windy conditions. Rainfall also affects surface temperature, though its influence is more subtle. Rainwater is often cooler than the ocean's surface, and heavy rainfall can temporarily lower temperature in localized areas. More importantly, rainfall alters salinity, which in turn affects how water layers interact. Fresher water is less dense than saltier water, so rain can create a thin, buoyant layer that traps heat near the surface for a short time before mixing occurs. Seasonal changes introduce another layer of complexity. In temperate regions, surface waters warm during spring and summer as days grow longer and sunlight intensifies. During autumn and winter, reduced sunlight and colder air temperatures cause the surface to cool. As water cools, it becomes denser and begins to sink, allowing deeper water to rise. This seasonal overturning redistributes heat vertically and plays a key role in nutrient cycling, but it also marks the beginning of a gradual separation between surface warmth and the colder depths below. Despite all this motion and change, the surface layer remains remarkably shallow compared to the ocean as a whole. The average depth of the global ocean is nearly 4,000 meters, yet most solar heating occurs within the top few dozen meters. Water absorbs light quickly, and even the clearest ocean water becomes dark with depth. Red wavelengths of light disappear first, followed by yellow and green, until only faint blue light penetrates deeper layers. Heat follows a similar pattern, concentrated near the top and diminishing rapidly with depth. This uneven distribution of heat creates a vertical temperature structure that defines the ocean. At the surface, temperature can fluctuate dramatically over short timescales. A passing storm can cool surface waters by several degrees in a matter of hours. A period of calm, clear weather can allow temperatures to rise just as quickly. These rapid changes stand in stark contrast to the slow, almost timeless thermal behavior of the deep ocean, where temperature shifts occur over centuries rather than days. Surface currents further complicate the picture. Driven by wind patterns and Earth's rotation, these currents transport warm and cold water across vast distances. Warm currents carry heat from the tropics toward higher latitudes, while cold currents move chilled water toward the equator. This horizontal movement of heat influences regional climates and shapes marine ecosystems. Areas influenced by warm currents tend to have higher surface temperatures and greater biological productivity, while regions dominated by cold currents often support unique, cold-adapted life. One of the most important surface currents is the global system that circulates water around the planet's oceans. Although its deeper components move slowly, the surface branches respond quickly to atmospheric conditions. Changes in wind strength or direction can alter current paths, shifting warm water away from some regions and toward others. These shifts can influence weather patterns, rainfall, and even long-term climate trends. Despite its variability, the surface layer performs a vital function. It acts as the interface between the ocean and the atmosphere, regulating the exchange of heat, moisture, and gases. Carbon dioxide dissolves into surface waters, where it can be transported to deeper layers through physical and biological processes. Oxygen enters the ocean through surface mixing, supporting life far below. Temperature plays a central role in all of these exchanges, influencing how gases dissolve and how quickly water mixes. The instability of surface temperature might suggest a chaotic environment, but there is an underlying order to these fluctuations. Physical laws govern how heat moves, how water layers interact, and how energy is conserved. The ocean does not heat endlessly at the surface, because excess energy is redistributed through mixing, evaporation, and radiation back into the atmosphere. This balance maintains a dynamic equilibrium, allowing the surface to respond to environmental changes without reaching extremes that would disrupt the entire system. As we move away from the surface, the influence of sunlight fades rapidly. The water becomes darker, colder, and more isolated from atmospheric forces. The sharp contrast between the warm, active surface and the cold, stable depths begins to emerge just tens of meters below. This transition marks the boundary between the world we know and the vast, hidden environment that makes up most of the ocean's volume. Understanding surface temperature is essential because it determines how heat enters the ocean in the first place. Every joule of thermal energy found in the deep sea can ultimately be traced back to processes that occur at or near the surface. Even the coldest abyssal waters were once at the surface, where they cooled, became dense, and slowly sank. The surface is where the story of deep ocean temperature begins, even though its influence becomes almost unrecognizable as we descend. As the sun sets and night falls, surface waters begin to release stored heat back into the atmosphere. This nightly cooling cycle repeats endlessly, a quiet rhythm that has persisted for millions of years. The deep ocean remains unaffected by these daily changes, insulated by layers of water above. This separation between fast-changing surface conditions and the slow, steady cold below is one of the defining characteristics of Earth's oceans. In the next stage of our descent, we will leave behind the restless surface and enter a region where temperature drops rapidly with depth. This zone, known for its sharp thermal gradient, acts as a barrier between the warm upper ocean and the cold interior. It is here that the ocean begins to reveal how temperature truly behaves when sunlight no longer reaches. For now, we remain at the surface, where heat is temporary, motion is constant, and change is the rule rather than the exception. This thin, energetic layer may seem insignificant compared to the ocean's immense depth, but it is the gateway through which all warmth must pass on its long journey into the silent, freezing world below. Sunlight, seasons, and daily temperature change. As time passes at the ocean's surface, temperature follows a quiet but persistent rhythm. Unlike the deep ocean, where change is measured in centuries, the surface responds almost immediately to the cycle of day and night. Each sunrise begins a slow warming, and each sunset starts a gradual release of heat back into the atmosphere. This daily exchange shapes the thermal personality of the upper ocean and explains why surface temperature is the most variable anywhere in the marine environment. When the sun rises, solar energy begins to penetrate the water almost instantly. The uppermost centimeters absorb the largest share of this radiation, warming first and most intensely. As the day progresses, heat spreads downward through a combination of molecular motion and gentle mixing caused by wind and waves. On calm days, when wind is minimal, this warming can create a thin layer of noticeably warmer water resting on top of cooler water below. This layering is temporary but important, as it influences how heat and gases move between the ocean and the air. By midday, surface temperature often reaches its daily maximum. In tropical oceans, this increase may be subtle, only a degree or two, while in enclosed seas or shallow coastal areas, the change can be more pronounced. The ocean's high heat capacity prevents extreme swings, but it does not eliminate variation entirely. The surface remains sensitive to atmospheric conditions, cloud cover, and wind speed, all of which can amplify or dampen warming. As evening approaches and sunlight weakens, the surface begins to cool. Heat flows back into the air through radiation and conduction, while evaporation continues to remove energy as water molecules escape into the atmosphere. This cooling increases the density of surface water slightly, encouraging gentle mixing with cooler layers beneath. By the time night fully arrives, the temperature difference between surface and subsurface waters is often reduced, restoring a more uniform upper layer. This daily cycle repeats endlessly, yet its effects rarely extend beyond the upper tens of meters. Below this depth, the ocean becomes increasingly insulated from short-term changes. The deeper layers remain largely unaware of whether it is day or night at the surface, reinforcing the idea that the ocean is divided into thermal worlds separated by depth. Seasonal changes introduce a slower but more powerful rhythm. As Earth orbits the sun, the angle and duration of sunlight change, altering how much energy reaches the ocean's surface. In summer, longer days and more direct sunlight allow the surface layer to absorb heat over extended periods. This gradual accumulation leads to warmer surface temperatures that can persist for months. In winter, shorter days and lower sun angles reduce incoming energy, allowing surface waters to cool steadily. In temperate regions, this seasonal pattern drives one of the most important processes in ocean temperature dynamics: seasonal mixing. During summer, warm, lighter water tends to remain at the surface, forming a stable layer that resists mixing with colder water below. As autumn arrives and surface cooling intensifies, this warm layer loses heat, becomes denser, and begins to sink. Wind and storms accelerate this process, mixing the upper ocean and redistributing heat downward. Winter often brings the most thorough mixing of the year. In some regions, surface waters cool enough to match the temperature and density of deeper layers, allowing the ocean to overturn vertically. This process not only transfers heat, but also brings nutrients from the depths to the surface, supporting marine life when sunlight returns in spring. From a thermal perspective, winter mixing represents one of the few times when surface temperature changes can influence deeper layers in a meaningful way. In polar regions, seasonal effects are even more pronounced. During summer, extended daylight allows surface waters to warm modestly, despite the low angle of the sun. In winter, Prolonged darkness and extreme cold cause surface temperatures to plummet, sometimes approaching the freezing point of seawater. Sea ice forms when surface water loses enough heat, creating an insulating layer that limits further heat loss from the ocean below. Sea ice plays a critical role in regulating surface temperature. Once formed, it reduces direct contact between the ocean and the atmosphere, slowing additional cooling. Beneath the ice, water temperatures stabilize just above freezing, creating a surprisingly steady environment compared to the volatile conditions above. This stability hints at the thermal behavior that dominates the deep ocean, where temperature remains nearly constant year-round. Latitude strongly influences how seasonal cycles affect surface temperature. Near the equator, seasonal variation is minimal, and daily cycles dominate. Surface temperatures remain warm throughout the year, with only slight changes driven by cloud cover and ocean currents. At higher latitudes, seasonal variation becomes more significant, with large differences between summer and winter temperatures. These gradients drive global circulation patterns that move heat from warmer regions toward colder ones. Ocean currents act as conveyors of seasonal heat. Warm surface waters formed during summer can be transported thousands of kilometers by currents before releasing their energy. This movement delays and redistributes seasonal effects, allowing regions far from the tropics to experience relatively mild conditions. Conversely, cold currents can carry chilled water toward lower latitudes, moderating surface temperatures and influencing local climates. Storms introduce short-term disruptions to these seasonal patterns. Strong winds associated with storms increase mixing, bringing cooler water to the surface and temporarily lowering temperature. Heavy cloud cover reduces incoming sunlight, limiting warming during the day. After a storm passes, the surface slowly returns to equilibrium, guided by the same daily and seasonal rhythms as before. Despite constant change, surface temperature follows predictable statistical patterns over long periods. Scientists can identify average seasonal cycles, long-term trends, and anomalies by observing these patterns across decades. This predictability allows surface temperature to serve as an indicator of broader climate behavior, even though it remains the most variable part of the ocean. The contrast between surface variability and deep stability becomes more striking as we consider time. A surface water parcel may experience thousands of heating and cooling cycles over a single year, responding to every sunrise, sunset, and passing weather system. Deep ocean water, by contrast, may remain at nearly the same temperature for hundreds or even thousands of years. This disparity underscores how quickly the surface responds to change and how slowly the ocean interior evolves. Surface temperature also influences how heat is stored in the ocean. During warm seasons, excess heat accumulates in the upper layers, some of which will eventually be transferred downward through mixing and circulation. This gradual transfer acts as a buffer, preventing sudden changes in global temperature. The ocean absorbs the majority of excess heat added to Earth's system, and the surface is the gateway through which that heat enters. As we prepare to descend further, the surface world begins to feel increasingly distant. The constant motion, daily cycles, and seasonal swings give way to a quieter environment below. Temperature no longer rises and falls with the sun, but instead follows a smooth, steady decline with depth. This transition begins just beneath the reach of surface mixing, where the influence of sunlight weakens and a more structured thermal profile emerges. In the next chapter, we will move below the surface layer and encounter the zone where temperature changes most rapidly with depth. Here, heat fades quickly, and the ocean begins to separate into layers that rarely interact. This boundary marks the true beginning of the deep ocean's thermal world, where cold becomes permanent and change slows almost to a stop. For now, the surface remains a place of motion and warmth, shaped by the rhythms of Earth's rotation and orbit. It is the ocean's most active thermal region, constantly adjusting, constantly exchanging energy, and quietly supplying heat to the vast, cold depths below. The first descent, entering the thermocline. As we move away from the surface, the ocean begins to change in subtle but decisive ways. The light softens, motion slows, and temperature no longer follows the familiar rhythm of day and night. Within the first few tens to hundreds of meters, we enter a region where heat disappears rapidly with depth. This transition zone is known as the thermocline, and it represents one of the most important boundaries in the ocean's thermal structure. The thermocline forms because sunlight does not heat the ocean evenly. Most solar energy is absorbed near the surface, while deeper water remains largely untouched by direct warming. Over time, this creates a sharp contrast between warm surface water and much colder water below. The thermocline sits between these two layers, acting as a steep temperature gradient rather than a single, clearly defined line. As depth increases within this zone, temperature can drop dramatically over a relatively short vertical distance. In many parts of the world, surface waters may be warm enough to feel comfortable to human skin, while just 100 meters below, temperatures can be several degrees colder. This rapid change is not gradual in the way one might expect. Instead, it feels as though the ocean suddenly releases its warmth, allowing cold to dominate. The thermocline is the ocean's first true threshold, separating the restless warmth of the surface from the calm cold below. The strength and depth of the thermocline vary depending on location and season. In tropical oceans, where surface heating is intense and consistent, the thermocline is often strong and well-defined. Warm water forms a thick surface layer, while cold water lies firmly beneath it. In temperate regions, the thermocline develops during warmer months and weakens or disappears during winter, when surface cooling and storms mix the water column more thoroughly. This seasonal behavior gives the thermocline a dynamic character. During summer, it acts as a barrier that limits vertical mixing. Warm, lighter water remains above, while cold, denser water stays below. Heat becomes trapped near the surface, reinforcing the temperature difference. As autumn arrives and surface waters cool, this barrier weakens. Cooling increases surface water density, allowing it to sink and mix with deeper layers, gradually erasing the thermocline until it forms again the following year. In calm conditions, the thermocline can be remarkably stable. Minimal wind and steady sunlight allow it to persist for weeks or even months. During this time, the ocean becomes strongly layered, with little exchange of heat between surface and depth. This stability contributes to the deep ocean's long-term cold, as very little surface heat penetrates beyond the thermocline under such conditions. Despite its stability, the thermocline is not impenetrable. Strong winds, storms, and large waves can disrupt it, temporarily mixing warm and cold layers. Internal waves, which move along density boundaries within the ocean, can also shift the thermocline up and down without breaking it. These slow, rolling motions are invisible from the surface, but play an important role in redistributing energy within the water column. Temperature changes within the thermocline influence many physical and biological processes. Because water density depends on temperature, the steep gradient creates a strong density contrast. This contrast resists vertical movement, making it difficult for water parcels to cross the boundary. As a result, nutrients from deeper water remain trapped below, while oxygen and heat from the surface struggle to move downward. This separation shapes marine ecosystems, concentrating life either above or below the thermocline depending on species adaptations. For temperature, the thermocline represents a turning point. Above it, heat behaves unpredictably, responding quickly to weather and sunlight. Below it, temperature begins to settle into a slow, steady decline. The deeper we descend within the thermocline, the less influence the surface has. Eventually, daily and seasonal signals fade entirely, replaced by a cold environment governed by long-term processes. The existence of the thermocline explains why the deep ocean remains cold even in a warming world. Most excess heat added to the climate system accumulates in the upper ocean. Only a fraction crosses the thermocline to reach deeper layers, and this transfer occurs slowly. The thermocline acts as a buffer, delaying the movement of heat into the ocean interior and preserving the deep sea's near freezing temperatures. In some regions, the thermocline is shallow, beginning just a few tens of meters below the surface. In others, especially in the open ocean, it may extend several hundred meters down. Its depth reflects a balance between surface heating, wind-driven mixing, and large-scale circulation. Where winds are strong and persistent, mixing can deepen the thermocline or blur it entirely. Where winds are weak and sunlight is intense, the thermocline remains sharp and shallow. As we continue our descent, the water grows noticeably colder. The sensation of warmth becomes distant, replaced by a quiet chill that feels constant and unchanging. Light dims further, and the ocean takes on a uniform darkness. This is the beginning of the thermal world that dominates most of the ocean's volume, a world defined by stability rather than fluctuation. Beyond the thermocline lies the realm where temperature changes slow dramatically. Here, heat is scarce, and the ocean's memory grows long. Water in these depths may have last contacted the surface hundreds of years ago, carrying with it the thermal signature of a distant place and time. The thermocline marks the last boundary where surface warmth still has a recognizable presence. In the next part of our journey, we will leave the thermocline behind entirely and enter deeper waters where temperature settles into a narrow range just above freezing. This environment, insulated from the surface and shaped by global circulation, represents the true thermal interior of the ocean. The rapid changes are over, and the deep sea's quiet cold begins to reveal itself. How heat disappears with depth. Below the thermocline, the ocean enters a different thermal reality. The rapid temperature drops that defined the upper layers begin to slow, and the influence of the surface fades almost completely. Heat does not vanish suddenly, but it becomes increasingly scarce, diluted across immense volumes of water. What remains is a gradual, steady decline toward the near-freezing temperatures that dominate the deep ocean. The disappearance of heat with depth is governed by simple physical limits. Sunlight, the primary source of oceanic warmth, cannot penetrate far into water. Even in the clearest seas, usable solar energy is absorbed within the upper few hundred meters. Below this range, the ocean receives virtually no direct heat from above. Without a constant source of energy, deeper layers rely on slow processes, mixing, circulation, and conduction to gain or lose heat. Conduction, the direct transfer of heat between molecules, plays only a minor role in the ocean. Water conducts heat far less efficiently than metals or solids, and the immense distances involved make conduction alone insignificant. Instead, heat moves primarily through the physical movement of water itself. When warm water sinks or cold water rises, heat is redistributed. But below the thermocline, vertical movement becomes rare and slow, limited by strong density stratification. Density is the key to understanding why heat struggles to move downward. As water cools, it becomes denser, but salinity and pressure complicate this relationship. In the deep ocean, cold, salty water is often denser than warmer, fresher water above it. This layering creates a stable arrangement that resists vertical mixing. Any attempt for warm water to move downward is opposed by buoyancy forces that push it back toward the surface. Pressure increases steadily with depth, but pressure alone does not generate heat in the ocean. Instead, it subtly alters the physical properties of water, including how temperature and density relate to one another. At great depths, water can remain liquid at temperatures below the normal freezing point, allowing the deep ocean to exist in a supercooled but stable state. This pressure-adjusted behavior further isolates deep water from surface warmth. As we descend, the rate of temperature change becomes almost imperceptible. Between 1,000 and 4,000 meters, temperature may decrease by only a few degrees. In many regions, it stabilizes between 1 and 4 degrees Celsius, remaining within this narrow range across vast areas of the seafloor. This consistency contrasts sharply with the variability of the surface and highlights how effectively the ocean interior is insulated from short-term change. The heat that does reach these depths arrives through large-scale circulation rather than direct transfer. Cold, dense water formed near the poles sinks and spreads across the ocean floor, carrying with it the thermal characteristics of its origin. This water mass moves slowly, driven by gravity and subtle pressure gradients, filling deep basins and trenches over centuries. The temperature it carries reflects the conditions at the surface where it last cooled and sank. Once in the deep ocean, this water changes very little. Isolated from sunlight and largely cut off from the atmosphere, it drifts in near darkness, slowly aging as it moves. Its temperature becomes a record of past climates, preserved with remarkable fidelity. In this way, the deep ocean acts as a thermal archive, storing information about Earth's history in its cold interior. Occasionally, heat does enter the deep ocean from below. Earth's interior releases geothermal energy through the seafloor, particularly along mid-ocean ridges and volcanic regions. This heat flux is real but extremely small compared to the energy received at the surface. Spread across the entire ocean floor, geothermal heating raises average deep ocean temperature by only a tiny fraction of a degree. It adds subtle complexity to the thermal landscape, but does not fundamentally warm the deep sea. Where geothermal heat is concentrated, such as near hydrothermal vents, local temperatures can be dramatically higher. Superheated water jets into the surrounding cold, creating sharp thermal contrasts over very short distances. Yet these environments are rare and isolated. Beyond a few meters from a vent, the surrounding water quickly returns to its near-freezing baseline. The vast majority of the deep ocean remains cold and uniform. Another factor influencing how heat disappears with depth is time. Even when conditions allow for heat transfer, the process is slow. A parcel of water leaving the surface may take hundreds or thousands of years to reach the deepest parts of the ocean. By the time it arrives, its temperature reflects long past surface conditions rather than the present climate. This delay creates a powerful buffering effect, smoothing rapid changes and preserving long-term stability. The ocean's immense volume amplifies this effect. More than 90% of ocean water lies below the thermocline, occupying depths where temperature changes are minimal. Any heat that does penetrate these depths is distributed across an enormous mass, diluting its impact. This is why the deep ocean warms so slowly, even as surface temperatures rise more quickly. As depth increases, biological activity decreases, and with it, one potential source of heat. In surface waters, living organisms absorb sunlight, metabolize energy, and release heat as a byproduct of life. In the deep ocean, life exists at a slower pace, with lower metabolic rates and sparse populations. The heat produced by biological processes is negligible compared to the surrounding cold, further reinforcing thermal stability. The absence of light and heat creates an environment where temperature becomes a defining constant rather than a variable. For deep-sea organisms, the cold is not a challenge to be endured occasionally, but a permanent condition. Evolution has shaped life to function efficiently at low temperatures, relying on slow chemical reactions and energy conservation. The stability of temperature allows these adaptations to persist without the need for constant adjustment. From a physical perspective, the deep ocean's cold represents the endpoint of heat's journey. Energy enters at the surface, is redistributed by currents and mixing, and gradually fades as it moves downward. By the time it reaches the abyss, it has lost almost all connection to its source. What remains is a quiet, uniform chill that defines the largest habitat on Earth. As we continue downward, the sense of depth becomes more pronounced. The water around us feels heavy and still, its temperature unchanging. There are no daily cycles here, no seasons, no sudden shifts. Heat has all but disappeared, leaving behind an environment governed by slow circulation and immense pressure. In the next stage of our descent, we will enter the deep ocean proper, where temperature stabilizes just above freezing across thousands of kilometers. Here, the ocean reveals its most enduring thermal character, a cold that has persisted for millions of years, shaping the planet in ways that are only now becoming fully understood. Entering the twilight zone, temperature between 200 and 1,000 meters. As we descend beyond the thermocline, the ocean enters a region where light weakens dramatically and temperature settles into a quieter pattern. This is often called the twilight zone, a vast middle layer stretching roughly from 200 to 1,000 meters below the surface. Here, the ocean is no longer warmed by direct sunlight, yet it is not fully part of the deep abyssal world either. Temperature continues to fall, but at a slower, more measured pace, signaling a transition from surface-driven change to long-term stability. In the upper reaches of the twilight zone, the last traces of surface influence can still be detected. Seasonal signals linger faintly, carried downward through mixing and circulation. However, these signals weaken rapidly with depth. By the time we reach several hundred meters, daily temperature cycles have vanished completely, and even seasonal variation becomes minimal. What remains is a gradual cooling trend that reflects the ocean's internal structure rather than external conditions. Typical temperatures in this zone vary depending on latitude and regional circulation, but they are consistently cooler than the surface. In tropical regions, water entering the twilight zone may still be relatively warm compared to polar oceans, yet it cools steadily as depth increases. By 1,000 meters, temperatures often approach 5 degrees Celsius or lower, regardless of the warmth above. This convergence toward cold illustrates how effectively the ocean interior resists surface heat. The fading of light and heat occur together. As sunlight diminishes, so does the energy available to warm the water. The blue glow that once penetrated from above grows dimmer, and with it, the last reminders of surface warmth disappear. Temperature becomes more uniform horizontally, varying less from place to place than it does near the surface. This uniformity marks the beginning of the ocean's vast cold interior. Density stratification remains important throughout the twilight zone. Although the steep temperature gradient of the thermocline has weakened, subtle differences in temperature and salinity continue to maintain layered structure. These layers slow vertical movement, limiting how much heat can cross from above. As a result, the twilight zone acts as a buffer, absorbing small amounts of heat while protecting the deeper ocean from rapid change. Currents still flow through this region, but they move more slowly than surface currents. These mid-depth currents transport water masses formed elsewhere, carrying their thermal characteristics across ocean basins. A parcel of water in the twilight zone may have originated near the surface at high latitudes, cooled there, and then slowly drifted equatorward. Its temperature reflects not the local surface conditions, but the distant environment where it last contacted the atmosphere. This slow movement contributes to the remarkable consistency of temperature within the twilight zone. While surface waters can warm or cool by several degrees in a single season, temperature here changes so gradually that differences may only become noticeable over decades. The ocean's memory lengthens with depth, and the twilight zone represents a midpoint between short-term variability and deep ocean permanence. For marine life, this thermal environment presents both challenges and opportunities. The cold slows chemical reactions and metabolic processes, encouraging energy efficiency and patience. Organisms living here are adapted to stable temperatures, relying on predictable conditions rather than rapid response. From a physical perspective, this biological stability mirrors the thermal stability of the water itself. As we approach the lower boundary of the twilight zone, temperature changes become increasingly subtle. The descent feels quieter, heavier, as though the ocean has settled into a steady state. The last remnants of surface-driven heat have been diluted beyond recognition, leaving behind water that is uniformly cold and largely isolated from the world above. Beyond this point lies the deep ocean proper, where temperature hovers just above freezing across immense distances. The twilight zone fades into darkness, and the ocean's thermal story becomes one of endurance rather than change. In the next part of our journey, we will cross this threshold and enter a realm where cold defines everything, from circulation to life itself, and where temperature remains almost unchanged for centuries at a time. For now, we linger in this middle world, suspended between warmth and cold, motion and stillness. The twilight zone stands as a reminder that the ocean does not shift abruptly from surface chaos to abyssal calm. Instead, temperature eases into stability, step by step, layer by layer, as we descend into the deep. Why the twilight zone feels cold but not frozen. As we continue deeper through the twilight zone, the ocean's temperature settles into a narrow range that feels consistently cold, yet rarely reaches the point of freezing. This balance is one of the most distinctive features of mid-depth waters. Despite the absence of sunlight and the increasing isolation from surface influence, the ocean here remains liquid, stable, and surprisingly uniform. Understanding why this zone stays cold but not frozen reveals much about how heat behaves in the ocean as a whole. Seawater freezes at a lower temperature than freshwater. The presence of dissolved salts interferes with the formation of ice crystals, lowering the freezing point to around -2 degrees Celsius. This simple chemical property has profound consequences. Even in the darkest, deepest parts of the ocean, temperatures often hover just above this threshold, allowing liquid water to persist under immense pressure. In the twilight zone, temperatures are typically several degrees warmer than this limit, creating an environment that is cold but far from solid. Pressure also plays a subtle role. As depth increases, pressure rises steadily, altering the physical behavior of water. High pressure allows water to remain liquid at temperatures that would otherwise lead to freezing near the surface. While pressure alone does not generate warmth, it expands the range of conditions under which liquid water can exist. This helps explain why the ocean remains fluid even in its coldest regions. The coldness of the twilight zone reflects its distance from direct heat sources. Sunlight no longer penetrates here, and geothermal heat from below remains faint and diffuse. What warmth exists arrives slowly through circulation, carried by water masses that formed elsewhere. These water masses cooled at the surface, sank, and traveled long distances before reaching this depth. Their temperature represents an average of past conditions rather than current surface warmth. Because heat input is limited, temperature variations are small. The twilight zone does not experience sudden cold snaps or warm surges. Instead, it maintains a steady chill, often ranging between 4 and 8 degrees Celsius depending on location. This consistency contrasts sharply with surface waters, which may warm or cool by similar amounts over a single day. Here, change is gradual, almost imperceptible. This stable cold has important consequences for how energy moves. Chemical reactions proceed more slowly at lower temperatures, reducing the rate at which heat is generated by biological activity. Organisms living here operate on tight energy budgets, producing minimal excess heat. As a result, biological processes contribute little to warming the surrounding water, reinforcing the cold environment. Water density remains a controlling factor. In the twilight zone, cold water is typically denser than the layers above, creating a stable arrangement that resists mixing. This stratification prevents warmer surface water from sinking easily and limits the upward movement of colder deep water. The result is a layered structure where temperature remains locked in place, changing only when large-scale circulation patterns shift. Occasionally, internal waves ripple through this zone, moving along density boundaries. These waves can shift layers up and down by tens of meters without breaking them apart. While they redistribute energy locally, they do not significantly alter average temperature. The cold remains, undisturbed over long periods, a quiet constant beneath the more active surface. The twilight zone's temperature also reflects its role as a transition region. It absorbs some heat from above, but releases little to the depths below. In this sense, it acts as a thermal filter, smoothing out variability and protecting the deep ocean from rapid warming. Any heat that does pass through is diluted and spread across enormous volumes, reducing its impact. From a human perspective, the cold here would feel intense, but not immediately life-threatening in the way freezing conditions might be. For deep-sea organisms, however, this temperature defines normality. Their physiology is tuned to this steady cold, with enzymes and cellular structures optimized for slow, efficient function. The lack of temperature extremes allows life to persist without constant adjustment. As we drift toward the lower boundary of the twilight zone, temperature changes become increasingly subtle. The descent feels less like moving through layers and more like settling into a uniform environment. The ocean's thermal personality becomes quieter, steadier, and more predictable. Below us lies the deep ocean proper, where temperature stabilizes just above freezing across most of the planet. The twilight zone marks the last region where temperature still declines noticeably with depth. Beyond it, the cold becomes nearly absolute, a defining feature of the abyss. In the next chapter, we will cross into those deep waters and explore why their temperature remains almost unchanged across vast distances and timescales. The variability of the upper ocean will fade entirely, replaced by a cold that has endured for millions of years. The deep ocean begins, temperature below 1,000 meters. As we pass beyond 1,000 meters, the ocean completes its transition into a world defined almost entirely by cold. The gradual cooling that began near the surface has slowed to a near standstill, and temperature now settles into a narrow, persistent range. This is the deep ocean proper, a realm that covers most of the planet's surface and holds the majority of its liquid water. Here, temperature no longer responds to weather, seasons, or even centuries in any noticeable way. Instead, it reflects processes that unfold over geological time. In most regions of the deep ocean, temperature stabilizes between 1 and 4 degrees Celsius. This range may seem narrow, but it represents a delicate balance shaped by global circulation, pressure, and the physical properties of seawater. Once water reaches these depths, it becomes largely isolated from the surface. The warmth of sunlight is long gone, and the slow pace of mixing ensures that whatever temperature exists here will persist for generations. The water filling the deep ocean did not originate locally. It was formed at the surface, usually in high-latitude regions where cold air and long winters strip heat from the sea. As surface water cools, it becomes denser and begins to sink, carrying its low temperature with it. Over time, this cold, dense water spreads outward and downward, filling deep basins across the globe. Its journey may take hundreds or thousands of years, but its temperature changes very little along the way. Once in place, deep ocean water moves slowly, guided by subtle differences in density and pressure. These movements form part of the global circulation system that connects all oceans. Unlike surface currents, which can travel rapidly and shift direction, deep currents are steady and deliberate. Their slow pace reinforces thermal stability, preventing sudden temperature changes and preserving the cold environment. Pressure increases dramatically at these depths, but it does not introduce warmth. Instead, it allows water to remain liquid at temperatures close to freezing. Combined with salinity, pressure ensures that the deep ocean stays fluid even in its coldest regions. This creates a stable backdrop against which all deep-sea processes occur, from circulation to the evolution of life. Because temperature varies so little, it becomes one of the most predictable features of the deep ocean. Measurements taken thousands of kilometers apart often show nearly identical values. This uniformity is striking when compared to the patchwork of temperatures found at the surface. In the deep ocean, geography matters less than history. The temperature reflects where the water came from and how long it has been isolated from the atmosphere. The stability of deep ocean temperature has important consequences for the planet. By storing cold water over immense volumes, the ocean acts as a long-term heat reservoir, absorbing and redistributing energy on timescales far longer than human lifetimes. Changes in surface climate may take centuries to influence these depths, and when they do, the effects are subtle and slow. For life, this environment demands extreme adaptation. The cold slows biological processes, favoring organisms with low metabolic rates and efficient energy use. Temperature does not fluctuate enough to provide cues for rapid change, so deep sea life evolves around constancy rather than variability. From a thermal perspective, the deep ocean is one of the most stable habitats on Earth. As we continue downward, the sense of stillness grows. Temperature becomes almost irrelevant as a variable, replaced by pressure and darkness as the defining forces. The deep ocean's cold is not dramatic or threatening. It is simply present, everywhere, all the time. It is the background condition against which all deep-sea activity unfolds. In the next part of our journey, we will explore how this cold remains so consistent over centuries and why even major changes at the surface struggle to disturb it. The deep ocean's temperature is not just low, it is enduring, a quiet constant in a changing world. Why deep ocean temperature barely changes over centuries? In the deep ocean, time behaves differently. Temperature here is not shaped by days, seasons, or even decades. Instead, it responds to processes so slow that a single human lifetime is barely enough to register any change at all. This remarkable stability is not accidental. It is the result of how water moves, how heat is stored, and how isolated the deep ocean is from the world above. Once water sinks into the deep ocean, it becomes part of a vast, slow-moving system. This system is often described as global circulation, but unlike surface currents, it does not rush. Deep water drifts at a pace measured in centimeters per second or less. A parcel of water entering the deep ocean today may not return to the surface for hundreds or even thousands of years. During that time, its temperature remains almost unchanged. The reason for this stability lies in the ocean's enormous heat capacity. Water can store a large amount of thermal energy without changing temperature very much. In the deep ocean, this effect is magnified by sheer volume. The abyss contains most of the ocean's mass, so any heat that reaches these depths is spread thinly across an immense body of water. Even significant amounts of energy produce only minimal temperature change. Isolation is another key factor. The deep ocean is effectively sealed off from the atmosphere by layers of water above it. Wind, sunlight, and weather systems cannot reach these depths. Without direct contact with the air, the deep ocean cannot quickly gain or lose heat. Instead, it relies on slow exchanges through circulation, which act like a dimmer switch rather than an on-off button for temperature. The cold water filling the deep ocean often originates near the poles. In these regions, surface waters cool dramatically during long winters. As they lose heat, they become dense enough to sink, sliding beneath warmer layers and descending into the depths. This process supplies the deep ocean with cold water that reflects polar conditions rather than global averages. Once formed, this water mass spreads slowly, maintaining its low temperature as it travels. Because this process happens continuously but slowly, the deep ocean is constantly refreshed with cold water. At the same time, warmer water rarely reaches these depths in significant quantities. The balance between slow replenishment and limited heat input keeps temperature remarkably steady. Even when surface temperatures rise, the effect is muted and delayed by the layers above. Another reason deep ocean temperature changes so slowly is the lack of mixing. Above the thermocline, wind and waves stir the water, redistributing heat quickly. Below it, mixing is weak. Density differences create a stable arrangement that resists vertical movement. Without strong mixing, heat cannot easily cross from warmer layers into colder ones. This barrier preserves the deep ocean's thermal character. Geothermal heat from Earth's interior does contribute energy, but its influence is subtle. Spread across the entire seafloor, this heat adds only a tiny amount to deep ocean temperature. It is enough to create localized warmth near vents and ridges, but insufficient to raise the overall temperature of the abyss. In most places, geothermal input is dwarfed by the cold carried in from polar regions. The result of all these factors is a thermal environment that acts as a long-term memory. The temperature of the deep ocean reflects conditions from the past more than the present. In some regions, deep water still carries the signature of climates that existed centuries ago. This makes the deep ocean a valuable archive for scientists studying Earth's history, but it also highlights how resistant it is to rapid change. From a physical standpoint, the deep ocean behaves like a slow-moving reservoir. Heat enters at the surface, trickles downward over long periods, and is absorbed without dramatic effect. This buffering capacity helps stabilize Earth's climate by absorbing excess heat, but it also means that once changes do reach the deep ocean, they are difficult to reverse. For life in the abyss, this constancy is the norm. Organisms evolve in an environment where temperature is one of the least variable factors. There are no seasonal cues, no sudden warming events, and no rapid cooling. This predictability allows life to adapt to narrow thermal ranges, trading flexibility for efficiency. As we linger in these depths, the sense of permanence becomes clear. The cold around us is not temporary. It has persisted through ice ages, warm periods, and shifts in Earth's climate system. While the surface world changes quickly, the deep ocean responds slowly, preserving a steady thermal backdrop. In the next chapter, we will explore the coldest parts of the ocean and how temperature behaves in polar regions where the deep ocean is born. There, the connection between surface cold and abyssal stability becomes most apparent, revealing why the deepest waters on Earth are also among the most enduring. Near freezing water, why the deep ocean stays just above ice. As we descend further into the ocean's interior, temperature approaches one of its most striking limits. Across vast regions of the deep sea, the water remains only a fraction of a degree above freezing. This near-frozen state is not a temporary condition or an extreme found only in isolated places. It is the normal thermal background of the deep ocean, covering millions of square kilometers and persisting year after year, century after century. To understand why the deep ocean stays so cold without turning to ice, we must return to the fundamental properties of seawater. Unlike freshwater, which freezes at 0 degrees Celsius, seawater freezes at a lower temperature. Dissolved salts disrupt the orderly formation of ice crystals, pushing the freezing point down to roughly -2 degrees Celsius. This small difference has enormous consequences. It allows the ocean to remain liquid in environments where temperatures would otherwise solidify water. In the deep ocean, temperatures commonly range between 1 and 2 degrees Celsius, sometimes slightly higher depending on location. This places the water safely above its freezing point, yet still cold enough to feel almost timeless. The difference between liquid and solid here is narrow but stable. Pressure further reinforces this stability, allowing liquid water to exist even under conditions that would seem extreme at the surface. Pressure increases steadily with depth, adding weight and altering how water behaves at the molecular level. While pressure does not warm the water, it changes the conditions under which freezing occurs. At great depths, the formation of ice becomes less favorable, even at very low temperatures. This combination of salinity and pressure ensures that the deep ocean remains fluid, cold, and remarkably uniform. Another reason the deep ocean stays just above freezing lies in how and where deep water forms. Most deep ocean water originates at high latitudes, particularly around Antarctica and the North Atlantic. In these regions, surface waters are exposed to cold air, long winters, and persistent winds that strip away heat. As the water cools, it becomes dense enough to sink, carrying its near-freezing temperature downward into the ocean's interior. Once this cold water sinks, it spreads slowly along the ocean floor, filling basins and trenches. Importantly, it does not continue cooling indefinitely. After sinking, it is insulated from the atmosphere and cut off from further heat loss. Its temperature becomes locked in, changing only slightly as it mixes with other deep water masses. This process sets a lower boundary for deep ocean temperature, one defined by the coldest surface conditions where sinking occurs. In most cases, surface water does not cool all the way to its freezing point before sinking. Ice formation often begins first, removing fresh water and increasing the salinity of the remaining liquid. This saltier water becomes denser and sinks while still slightly above freezing. The result is deep water that is extremely cold but not frozen, maintaining a narrow thermal margin that persists across the global ocean. Geothermal heat from below provides a subtle counterbalance to this cold. Earth's interior releases energy through the seafloor, adding a faint warmth to the surrounding water. Although this heat is small compared to surface inputs, it is constant. Spread over vast areas, it helps prevent temperatures from dropping further, reinforcing the deep ocean's tendency to hover just above its freezing point rather than crossing it. The near-freezing temperature of the deep ocean has profound effects on how water moves. Cold water is dense, and this density drives the slow circulation that connects the world's oceans. Once formed, deep water flows along the bottom, guided by seafloor topography and pressure differences. Its temperature remains stable as it travels, changing only when it eventually rises toward the surface, far from its point of origin. For deep-sea life, this thermal environment defines existence. Organisms here are not adapted to warmth or variation. Instead, they are built for consistency. Enzymes function efficiently at low temperatures, metabolic rates are slow, and energy is conserved with precision. The near-freezing water is not a challenge to be overcome repeatedly, but a constant condition that shapes every aspect of biology. From a physical perspective, the deep ocean's cold acts as a stabilizing force for the planet. By holding such a large volume of water at low temperature, the ocean stores immense amounts of cold energy. This storage moderates Earth's climate by absorbing heat over long timescales and releasing it slowly. The near-freezing abyss acts as a thermal anchor, resisting rapid shifts and smoothing extremes. As we move deeper still, temperature changes become almost undetectable. The water around us feels uniform, heavy, and still. There are no gradients to cross, no sudden drops or rises. Cold has become the default state, a quiet presence that fills the ocean's deepest spaces. In the next part of our journey, we will explore how salinity and pressure work together to fine-tune this balance, controlling exactly how cold the deep ocean can become. There, we will see how chemistry and physics combine to keep Earth's largest environment locked in a state of cold stability, just shy of ice, for millions of years. Salt, pressure, and the freezing point of the deep ocean. As the deep ocean settles into its near-freezing state, two invisible forces quietly determine how cold the water can become without turning to ice. These forces are salinity and pressure. Together, they shape the thermal limits of the ocean's deepest layers, controlling the delicate balance between liquid water and solid ice in a world of darkness and immense weight. Salinity is the first and most important factor. Seawater is not pure water. It contains dissolved salts, primarily sodium chloride, along with many other minerals. These dissolved substances interfere with the ability of water molecules to arrange themselves into the orderly crystal structure required for ice to form. As a result, seawater freezes at a lower temperature than freshwater. On average, ocean water freezes at around -2 degrees Celsius, though this value can vary slightly depending on exact salt concentration. In the deep ocean, salinity is relatively uniform compared to surface waters. Rainfall, evaporation, and river input affect surface salinity, but these influences fade with depth. Once water sinks and becomes part of the deep ocean, its salinity changes very little. This consistency helps maintain a stable freezing point across vast regions of the seafloor. The water remains cold, but its chemistry prevents it from freezing under normal conditions. Pressure adds another layer of stability. With every 10 meters of depth, pressure increases by roughly 1 atmosphere. By the time we reach several thousand meters, the weight of the water above is immense. This pressure alters the physical behavior of water molecules, expanding the range of temperatures at which liquid water can exist. Although pressure alone does not warm the ocean, it makes freezing less likely at depth, even when temperatures are extremely low. The combined effect of salinity and pressure creates a safety margin. Deep ocean temperatures typically remain 1 to 2 degrees above the freezing point of seawater. This narrow gap is maintained by the balance between cold water formation at the surface and the small but constant input of heat from below. The ocean rarely approaches the exact conditions needed for ice to form at depth, and when it does, the situation is highly localized and temporary. One place where this balance becomes especially important is beneath polar sea ice. In regions near Antarctica and the Arctic, surface waters can cool to near their freezing point. As ice forms, salt is expelled into the surrounding water, increasing its salinity and density. This dense, salty water sinks, carrying its cold temperature into the deep ocean. Yet even here, freezing occurs only at the surface. Below, pressure and salinity ensure that the descending water remains liquid. This process explains why ice does not accumulate on the seafloor despite the extreme cold. The deep ocean is not a place where ice grows downward from the surface. Instead, it is filled with liquid water that has been chilled, concentrated, and stabilized by physical laws. The absence of ice allows circulation to continue, connecting the coldest regions of the planet to warmer ones over long timescales. Salinity also affects how temperature and density interact. In freshwater, cooling always increases density until freezing occurs. In seawater, the relationship is more complex. Changes in salinity can offset changes in temperature, allowing water to become denser without becoming colder. This complexity plays a crucial role in deep water formation and helps explain why the ocean can sustain such cold temperatures without crossing into a frozen state. Pressure further complicates the picture by modifying the freezing curve of seawater. At greater depths, the freezing point decreases slightly, making ice formation even less likely. This effect is subtle but significant over the vast pressures of the abyss. It ensures that even in the coldest trenches, where temperatures hover near the lower limit, liquid water remains the dominant phase. From a thermal perspective, this balance creates a remarkably stable environment. The deep ocean's temperature does not drift toward freezing because the conditions that would allow ice to form are rarely met simultaneously. Instead, the ocean remains locked in a narrow thermal range, cold but fluid, stable but dynamic enough to circulate slowly around the globe. For deep-sea organisms, this stability is essential. Ice formation would be catastrophic, disrupting circulation and destroying habitats. The chemistry and physics of seawater prevent this outcome, allowing life to persist in a cold but predictable environment. Organisms evolve around this constancy, relying on the assurance that temperature will not suddenly cross a critical threshold. As we continue our descent toward even greater depths, the influence of salinity and pressure remains constant. The water grows no colder in any dramatic sense. Instead, it settles into a quiet equilibrium, where the limits of temperature are defined not by chance, but by fundamental properties of the ocean itself. In the next chapter, we will turn our attention to the polar regions, where the coldest deep waters on Earth are born. There, we will see how surface conditions, salt, and pressure combine to produce the deep ocean's enduring chill, and how this process shapes the global temperature structure of the seas. Polar deep oceans, where the cold is born. To understand why the deep ocean is as cold as it is, we must travel not downward, but outward toward the polar regions of Earth. It is here, near the Arctic and Antarctica, that the coldest deep waters on the planet are formed. These regions act as gateways between the atmosphere and the abyss, shaping the temperature of the deep ocean far more than tropical warmth ever could. In polar oceans, the surface is exposed to some of the harshest conditions on Earth. Long winters, weak sunlight, and persistent cold winds strip heat from the water continuously. Unlike tropical regions, where sunlight replenishes surface warmth year-round, polar seas lose far more heat than they gain. Over time, this imbalance cools surface waters to near their freezing point. As surface water cools, it becomes denser. In fresh water, cooling eventually leads to freezing at the surface. In seawater, the process is different. As ice begins to form, salt is expelled into the surrounding water. This process increases the salinity and therefore the density of the remaining liquid water. The result is a heavy, extremely cold, salty water mass that sinks beneath the surface instead of freezing in place. This sinking marks the birth of deep ocean water. In the Southern Ocean surrounding Antarctica, this process is particularly intense. Vast quantities of cold, dense water descend along the continental shelf and spread outward across the ocean floor. This water, known for its extreme cold and high density, fills the deepest basins of the world's oceans and forms the backbone of global deep circulation. In the North Atlantic, a similar process occurs, though on a smaller scale. Cold air masses moving over the ocean cool surface waters, especially during winter. As heat is lost and salinity increases, dense water forms and sinks, contributing to the deep ocean's cold reservoir. Together, these polar regions supply most of the cold water that defines deep ocean temperature worldwide. Once this water sinks, it becomes largely isolated from the atmosphere. Its temperature is set at the moment of formation and changes very little afterward. The deep ocean does not generate its own cold. It inherits it from the surface conditions of polar seas. This inheritance explains why the deep ocean remains cold, even beneath tropical regions thousands of kilometers away. The journey of this polar water is slow and deliberate. After sinking, it spreads along the seafloor, guided by gravity and the shape of ocean basins. Its movement is measured in centimeters per second, yet over centuries, it travels vast distances. As it moves, it mixes gently with other deep waters, smoothing out temperature differences and creating the uniform cold found across the abyss. Because this process is continuous, the deep ocean is constantly renewed with cold water. Even as some deep water slowly rises elsewhere, new cold water forms at the poles to replace it. This slow turnover ensures that the deep ocean remains anchored to polar temperatures rather than surface averages. The cold produced in polar regions is not extreme enough to freeze the deep ocean, but it is sufficient to maintain temperatures just above freezing. The balance between heat loss at the surface and the physical limits imposed by salinity and pressure sets the lower boundary for deep ocean temperature. This boundary has remained remarkably stable over geological time. As we descend further into the deep ocean, the influence of these polar origins becomes increasingly clear. The cold around us is not random or local. It is the product of distant winds, ice formation, and long winters near the ends of the earth. Every degree of cold in the abyss carries the signature of those regions where surface and deep ocean are most closely connected. In the next part of our journey, we will explore how this cold spreads throughout the global ocean and how slow circulation links the polar seas to every deep basin on the planet. There, the deep ocean reveals itself not as a static body of water, but as a slowly moving, temperature-regulated system that spans the entire Earth. How cold polar water fills the global ocean. Once cold, dense water forms in the polar regions, its journey has only just begun. What follows is one of the slowest and most far-reaching movements on Earth, a deep circulation that carries near-freezing water from the poles into every major ocean basin. This process does not happen quickly or dramatically. Instead, it unfolds quietly over centuries, shaping the temperature of the deep ocean with remarkable consistency. After sinking near the polar margins, cold water begins to spread outward along the seafloor. Gravity guides this movement, pulling dense water into deeper basins where it can settle and expand. The seafloor itself acts like a system of channels and plains, steering the flow along predictable paths. Mountain ranges, ridges, and trenches influence where the water can go, but they do not stop its progress. Over time, the cold finds its way into nearly every corner of the deep ocean. This movement is part of a global system, often described as deep circulation. Unlike surface currents driven by wind, deep circulation is powered by differences in density. Cold, salty water sinks, while slightly warmer or fresher water rises elsewhere. The result is a slow but continuous exchange that links polar regions to the deep tropics and beyond. Temperature is the defining characteristic carried along this path. As cold water spreads, it mixes gently with existing deep water. This mixing is subtle, occurring through slow diffusion and weak turbulence rather than vigorous motion. The effect is to smooth out temperature differences, producing the uniform cold conditions observed across much of the deep ocean. By the time polar water has traveled thousands of kilometers, its temperature may have changed only slightly, diluted by mixing but still recognizably cold. The timescales involved are immense. Some deep waters may take 500 to 1,000 years to complete their journey through the global ocean. During this time, they remain isolated from the atmosphere, protected by layers above that prevent rapid heat exchange. This isolation ensures that deep ocean temperature reflects past surface conditions rather than present ones, reinforcing long-term stability. As deep water slowly moves, it eventually begins to rise in other regions. This upward motion is even slower than sinking, driven by gradual mixing and subtle density changes. When deep water finally returns toward the surface, it often does so far from where it originated, completing a global loop that connects distant parts of the planet. The temperature it carries has been preserved for centuries, only slightly altered by its long journey. This circulation plays a critical role in maintaining the deep ocean's cold. Without continuous input of polar water, deep temperatures would gradually drift upward due to geothermal heat and limited mixing from above. The steady supply of cold water counteracts these influences, keeping the abyss anchored near its current thermal state. The spread of polar water also explains why deep ocean temperature is surprisingly similar beneath very different surface climates. Whether beneath tropical seas or polar ice, deep waters often share nearly identical temperatures. The deep ocean is not warmed locally from above, but filled globally from below, supplied by cold sources that dominate its thermal character. Over geological timescales, changes in polar climate can alter this system. During colder periods in Earth's history, more cold water formed and sank, potentially cooling the deep ocean further. During warmer periods, the formation of deep water may have slowed, allowing temperatures to rise slightly. Even so, these changes occurred slowly, preserving the deep ocean's role as a stabilizing influence rather than a rapidly shifting one. For the planet as a whole, this slow circulation acts as a temperature regulator. By moving cold water into the depths and redistributing heat gradually, the ocean dampens extremes and delays rapid change. The deep ocean becomes a reservoir not just of cold, but of time itself, stretching the influence of surface conditions across centuries. As we drift within this moving cold, the sense of scale becomes clear. The temperature surrounding us is not the product of a single place or moment, but the outcome of a global process spanning oceans and eras. Each degree of cold represents countless winters near the poles, countless years of slow motion along the seafloor. In the next chapter, we will explore exceptions to this cold uniformity, places where heat intrudes into the deep ocean from below. There, sudden temperature contrasts emerge against the abyssal cold, revealing how rare and localized warmth truly is in the depths of the sea. Hydrothermal heat. Why the deep ocean is cold, but not everywhere. For most of the deep ocean, cold is absolute and uninterrupted. Temperatures hover just above freezing, uniform across enormous distances. Yet there are rare places where this pattern breaks, where heat rises from below instead of fading with depth. These places are few, isolated, and fleeting, but they reveal an important truth about the deep ocean. While it is overwhelmingly cold, it is not completely without warmth. The source of this deep ocean heat lies beneath the sea floor. Earth's interior remains hot, warmed by radioactive decay and the residual heat of planetary formation. In most places, this heat escapes slowly and evenly through the crust, contributing only a tiny amount of warmth to the surrounding water. Spread across the vast area of the ocean floor, this geothermal energy is barely noticeable. It raises deep ocean temperature by only a fraction of a degree and does not disrupt the cold stability of the abyss. In certain regions, however, the Earth's crust is thinner or fractured. Along mid-ocean ridges, volcanic arcs, and tectonic boundaries, heat escapes more efficiently. Seawater seeps into cracks in the sea floor, is heated deep within the crust, and then rises back into the ocean. When this superheated water emerges, it creates what are known as hydrothermal vents. The temperature contrast at these vents is extreme. Water emerging from a vent can reach hundreds of degrees Celsius, far hotter than boiling water at the surface. Yet this heat exists in immediate contact with near-freezing deep ocean water. The result is a dramatic but highly localized temperature gradient. Just meters away from a vent, the surrounding water returns to its usual cold state, as if the heat had never been there at all. This rapid dissipation highlights how effective the deep ocean is at absorbing and dispersing heat. The immense volume of cold water surrounding a vent acts as a thermal sink, drawing heat away almost instantly. Unlike surface environments, where warmth can linger and spread, deep ocean heat fades quickly, overwhelmed by the surrounding cold. Hydrothermal systems do not warm the deep ocean in any meaningful, large-scale way. They are too few, too isolated, and too localized. While they introduce bursts of energy into otherwise cold regions, their influence is confined to small areas around the vent openings. Beyond these narrow zones, the deep ocean remains unchanged, its temperature steady and near freezing. The existence of these hotspots reveals an important balance. The deep ocean is cold, not because heat is entirely absent, but because cold dominates so completely. Geothermal input is constant but weak, while polar-derived cold water is abundant and persistent. The cold wins not through intensity, but through volume and time. These rare pockets of warmth also demonstrate how stable the deep ocean is overall. Even with superheated water pouring in from below, the average temperature of the abyss barely shifts. The system absorbs and neutralizes thermal extremes with ease, maintaining its long-term equilibrium. For life, hydrothermal vents create islands of opportunity in an otherwise energy-poor environment. Here, heat supports chemical reactions that form the basis of unique ecosystems. But even these ecosystems exist against a backdrop of cold. Their warmth is relative, defined by contrast rather than abundance. Beyond the immediate vicinity of a vent, the deep ocean quickly returns to its familiar chill. From a broader perspective, hydrothermal heat serves as a reminder that the deep ocean is connected to the planet's interior as well as its surface. Temperature in the abyss reflects not just atmospheric conditions and polar winters, but also the slow, steady pulse of Earth itself. Yet this influence is subtle, woven into the background rather than dominating it. As we drift away from these rare, warm zones, the ocean once again becomes uniform. Darkness deepens, movement slows, and temperature settles back into its narrow range. The warmth behind us fades completely, absorbed by the surrounding cold, leaving no trace of disturbance. In the next part of our journey, we will look more closely at what happens when deep ocean temperature changes suddenly over very short distances, and why such extremes remain isolated rather than spreading. There, we will see just how powerful the ocean's cold stability truly is, sudden temperature extremes, and why they never spread. In the deep ocean, sudden changes in temperature are rare. The environment is defined by gradual transitions and long-term stability. Yet, in a few isolated places, temperature can change dramatically over distances of only a few meters. These extremes stand in sharp contrast to the surrounding cold, and their behavior reveals just how resistant the deep ocean is to thermal disruption. Near hydrothermal vents, temperature gradients are among the steepest found anywhere on Earth. Superheated water pours out of the seafloor, sometimes hot enough to melt metals, while the surrounding ocean remains just above freezing. The difference between these two states can exceed several hundred degrees Celsius. Despite this, the warmth does not spread outward in any lasting way. Instead, it is absorbed and diluted almost immediately. The reason lies in the deep ocean's immense capacity to absorb heat. Cold water surrounds these vents on all sides, acting as a thermal sink that draws energy away as soon as it appears. The hot fluid rising from a vent mixes rapidly with the cold, losing heat through turbulence and diffusion. Within moments, the temperature drops sharply, and within meters, it becomes indistinguishable from the background cold. Density also plays a role in containing these extremes. Heated water becomes less dense and rises, pulling away from the seafloor rather than spreading laterally. As it rises, it mixes with colder water and cools rapidly. This upward movement prevents heat from accumulating or traveling far across the ocean floor. The deep ocean's stratification ensures that warmth is lifted and dispersed rather than allowed to pool. Another factor limiting the spread of heat is time. Hydrothermal activity is often intermittent. Vents can change intensity, shift location, or shut down entirely over geological timescales. Even when active, the heat they release is fleeting compared to the vastness of the surrounding ocean. There is simply not enough sustained energy to overcome the cold stability of the abyss. These sudden temperature extremes highlight a fundamental principle of deep ocean physics. Local disturbances do not easily alter global conditions. The deep ocean behaves like a massive buffer, smoothing out variations and preserving its thermal character. This buffering is so effective that even dramatic events leave no lasting imprint beyond their immediate surroundings. From a biological perspective, these isolated extremes create unique habitats without threatening the broader ecosystem. Organisms adapted to vent environments thrive in the warmth and chemical energy available there, while nearby regions remain unchanged. The separation between hot and cold allows diverse life strategies to coexist within a few kilometers of each other, all governed by stable temperature boundaries. The contrast between vent heat and abyssal cold also reinforces how rare warmth truly is at depth. For every square meter of seafloor influenced by hydrothermal activity, millions remain uniformly cold. The deep ocean's average temperature is not shaped by these extremes, but by the slow, steady processes that dominate its vast interior. As we move away from these rare disturbances, temperature becomes once again predictable and unchanging. The water feels heavy, still, and uniformly cold. The deep ocean reasserts its identity as a place where extremes are temporary and stability is permanent. In the next chapter, we will turn our attention to life itself and explore how organisms survive and thrive in near-freezing water. There, temperature becomes not just a physical condition, but a powerful force shaping biology in one of Earth's most enduring environments. Life in the cold. How deep-sea creatures survive near freezing temperatures. In the deep ocean, temperature is not something that changes or surprises. It is a constant presence, hovering just above freezing, shaping every aspect of life that exists there. For organisms living in this environment, survival depends not on resisting the cold, but on being perfectly adapted to it. The deep sea is not a place of struggle against temperature, it is a place of long-term adjustment, where biology and physics have reached a quiet agreement. Cold water slows everything. Chemical reactions proceed more gradually, muscles contract more slowly, and metabolism operates at a reduced pace. In the deep ocean, this slowing is not a disadvantage, but a defining feature of life. Energy is scarce at depth, and cold temperatures help conserve it. By operating slowly, deep-sea organisms minimize the energy they need to survive, aligning their biological rhythms with the unchanging cold around them. One of the most important adaptations to near-freezing temperatures is enzyme efficiency. Enzymes are the molecular machines that drive all biochemical reactions. In cold environments, standard enzymes would work too slowly to sustain life. Deep-sea organisms produce specialized enzymes that remain flexible and active at low temperatures, allowing essential processes to continue even in near-freezing water. These enzymes are finely tuned, operating efficiently within a narrow thermal range that matches the deep ocean's stability. Cell membranes also reflect adaptation to cold. In warmer environments, membranes can become too fluid, while in cold conditions, they risk becoming rigid and brittle. Deep-sea organisms adjust the composition of their cell membranes, incorporating specific lipids that maintain flexibility at low temperatures. This ensures that nutrients, gases, and signals can move across cell boundaries without disruption, even after centuries of exposure to cold. Metabolism in the deep ocean is slow but steady. Many organisms grow slowly, reproduce infrequently, and live long lives compared to their shallow water relatives. This slow pace mirrors the environment itself, where change is rare and resources arrive unpredictably. Near-freezing temperatures reduce metabolic demand, allowing life to persist on minimal energy input. Muscle function in cold water presents another challenge. Low temperatures reduce muscle power and speed, yet many deep-sea animals are capable of movement when needed. They achieve this through muscle structures adapted for efficiency rather than speed. Sudden bursts of motion are rare, but slow, deliberate movements are sufficient in an environment where prey and predators alike operate under the same thermal constraints. Nervous systems are also shaped by the cold. Signal transmission slows at low temperatures, affecting reaction times and sensory processing. Deep-sea organisms compensate by relying less on rapid responses and more on sensitivity and anticipation. Many species detect chemical signals or faint vibrations, allowing them to respond gradually rather than instantly. This sensory strategy aligns with a world where nothing happens quickly. The stability of deep ocean temperature plays a crucial role in these adaptations. Because temperature varies so little, organisms do not need to cope with thermal extremes or sudden shifts. Evolution favors specialization over flexibility. Deep-sea species are often highly adapted to their specific thermal niche, thriving within a narrow range that would be inhospitable to most surface-dwelling life. Reproduction in near-freezing water reflects the same principles. Development is slow, and life cycles are extended. Eggs and larvae may take months or even years to develop fully. Cold temperatures reduce developmental rates, but they also reduce mortality by limiting the pace of environmental change. In the deep ocean, patience is a successful strategy. The cold also influences how food is processed and stored. Digestion occurs slowly, extracting maximum energy from scarce resources. Many deep-sea organisms can go long periods without feeding, relying on efficient energy storage and minimal metabolic loss. Near-freezing temperatures make this possible by reducing the baseline energy cost of survival. Even behavior is shaped by temperature. In the deep ocean, there is little need for rapid movement or frequent activity. Many animals remain still for long periods, conserving energy until an opportunity arises. The cold supports this stillness, allowing organisms to exist in a state of low activity without harm. From an ecological perspective, the cold creates a balanced system. Predation occurs, but at a slower pace. Growth is limited, but so is competition. The entire ecosystem operates under the same thermal rules, creating a stable, if sparse, web of life. Temperature acts as a unifying factor, shaping interactions in a way that promotes long-term persistence rather than rapid turnover. The adaptations seen in deep-sea life highlight how temperature can define an environment more completely than any other factor. In the near-freezing depths, life does not fight the cold. It embraces it, evolving in harmony with a temperature that has remained unchanged for millions of years. As we move forward, we will explore how this cold environment influences not just individual organisms, but entire ecosystems, and how temperature stability allows life to persist in one of the most enduring habitats on Earth. Slow metabolism and cold-adapted biology. In the deep ocean, temperature does more than set the physical conditions of the environment. It governs time itself. Near-freezing water slows biological processes so thoroughly that life unfolds on a different schedule, one measured not in moments or seasons, but in years and decades. This slow biological rhythm is not a weakness. It is the foundation upon which deep-sea ecosystems are built. Cold temperatures reduce the rate of chemical reactions inside living cells. In warm environments, molecules collide frequently and reactions proceed quickly. In near-freezing water, molecular motion slows and reactions take longer to complete. For surface organisms, this slowdown would be debilitating. For deep-sea life, it is the norm. Evolution has reshaped physiology to function efficiently under these conditions, turning slowness into stability. Metabolism in the deep ocean operates at a fraction of the rate seen at the surface. Energy consumption is minimal, allowing organisms to survive on scarce and irregular food supplies. Many deep-sea animals can endure long periods without feeding, relying on stored energy and low metabolic demands. Cold temperatures make this possible by reducing the energy required simply to stay alive. Growth is slow, sometimes astonishingly so. Some deep-sea fish, corals, and invertebrates grow only millimeters per year. Yet this slow growth is accompanied by long lifespans. Individuals may live for decades or even centuries, their bodies shaped by a world where time moves gently. Temperature stability ensures that these long lives are not disrupted by sudden environmental changes. Cold-adapted biology also influences how organisms allocate energy. Rather than investing in speed, rapid reproduction, or aggressive competition, deep-sea life emphasizes efficiency. Energy is directed toward maintenance and survival rather than constant growth. This strategy fits perfectly with an environment where food arrives unpredictably and temperature never offers a boost to metabolic rate. Reproductive strategies reflect the same principle. In cold water, development is slow, but survival rates can be higher because conditions remain stable. Eggs and larvae drift in a predictable thermal environment, free from the temperature shocks common in surface waters. This predictability allows reproduction to succeed even when it unfolds over long periods. Cold also affects how organisms interact with their environment. Many deep-sea species have soft, gelatinous bodies that require little energy to maintain. These forms are well suited to cold water, where buoyancy and pressure reduce the need for rigid support structures. Temperature, pressure, and energy efficiency converge to shape life into forms rarely seen elsewhere. Enzymatic adaptations remain central to this slow biology. Proteins are structured to remain flexible at low temperatures, preventing them from becoming rigid and inactive. These adaptations are finely balanced. A small increase in temperature could destabilize these enzymes, while a decrease could slow them too much. The deep ocean's stable cold provides the narrow window in which such specialization can persist. The nervous systems of deep-sea organisms reflect the same slow pace. Signal transmission is reduced, reaction times are longer, and behaviors unfold gradually. This is not a disadvantage in a world where predators and prey alike move slowly and opportunities are rare. Cold sets the tempo for every interaction, ensuring that no organism gains an overwhelming advantage through speed alone. Over millions of years, this slow biological rhythm has created ecosystems that change very little over time. Species turnover is low, extinction rates are modest, and evolutionary change proceeds gradually. Temperature stability acts as a stabilizing force, preserving lineages that might struggle in more variable environments. The deep ocean thus becomes a refuge of persistence. While surface ecosystems respond quickly to climate shifts, storms, and seasonal cycles, deep-sea communities remain largely unchanged. Their cold environment shields them from rapid change, allowing life to continue much as it has for geological ages. As we move onward, we will turn our attention to the coldest places of all the deepest basins and trenches where temperature reaches its lowest stable limits. There, we will see how cold, pressure, and isolation combine to create some of the most enduring environments on Earth, places where temperature has remained nearly constant since long before humans existed. The coldest places in the ocean: basins, abyssal plains, and trenches. As we descend toward the deepest parts of the ocean, temperature reaches its most stable and enduring state. These regions, the abyssal plains and the great oceanic trenches, are among the coldest environments on Earth. Here, the ocean's thermal story reaches its quiet conclusion. The warmth of the surface has long since disappeared, and even the subtle gradients of mid-depth waters fade into near uniformity. Abyssal plains stretch across vast portions of the ocean floor, lying between 3,000 and 6,000 meters below the surface. Despite their immense size, their temperature varies very little. Across thousands of kilometers, the water resting above these plains often differs by less than a single degree. Typical temperatures range from about 1 to 2 degrees Celsius, rarely straying outside this narrow band. This consistency reflects the deep ocean's isolation from surface influence and the dominance of polar-derived water masses. The cold here is not sharp or biting in the way we might imagine cold on land. Instead, it is soft, pervasive, and constant. There are no cold fronts, no sudden drops, no seasonal cycles. The temperature surrounding the abyssal plains has likely remained within the same narrow range for thousands of years. In this environment, cold is not an event, it is a condition. Trenches represent the deepest places in the ocean, plunging far below the abyssal plains into depths exceeding 10,000 meters in some locations. Despite their extreme depth, temperatures in trenches are often only slightly colder than those above the surrounding plains. Pressure increases enormously, but temperature does not fall dramatically. In many trenches, water temperatures remain just above 1 degree Celsius, occasionally dipping slightly lower, but rarely approaching the freezing point. This may seem surprising. One might expect greater depth to bring colder conditions, but by the time water reaches these depths, most of its cooling has already occurred. The deep ocean has reached its thermal equilibrium long before the trench floor appears. Additional depth adds pressure, not cold. Temperature has already settled into its final range, defined by polar water formation and long-term circulation. The coldest deep ocean waters are often found not in the deepest trenches, but in basins where dense polar water can accumulate and remain undisturbed. These basins act as reservoirs, holding cold water that may remain isolated for centuries. Here, temperature reflects the coldest surface conditions from which the water originated, preserved almost unchanged by time. Because movement is so slow in these regions, heat exchange is minimal. The water resting in deep basins and trenches may have last been at the surface during a distant climate era. Its temperature is a snapshot of the past, carried forward into the present. This makes the deepest ocean one of the most thermally conservative environments on the planet. Geothermal heat continues to seep upward through the seafloor even here, but its influence remains subtle. Spread across vast areas and diluted by immense volumes of cold water, it does little to raise overall temperature. Even in the deepest trenches, the background cold dominates completely. For life, these coldest regions demand the greatest specialization. Organisms here are adapted not only to near-freezing temperatures, but to extreme pressure and isolation. Yet temperature remains one of the most predictable aspects of their world. In a place where everything else feels extreme, the cold is reliable, unchanging, and familiar. As we drift across the abyssal plains and down into the trenches, the sense of permanence becomes overwhelming. Temperature no longer changes with depth in any meaningful way. The ocean has reached its cold limit, a stable endpoint shaped by physics, chemistry, and time. In the next and final chapter, we will explore why these cold regions can remain unchanged for millions of years and what this stability means for Earth's climate and future. The journey downward is nearly complete, and the ocean's quiet cold has revealed its deepest secret: endurance. Why some deep ocean regions stay cold for millions of years. In the deepest parts of the ocean, cold is not just persistent, it is ancient. Some regions of the abyss have maintained nearly the same temperature for millions of years, surviving ice ages, warming periods, and dramatic shifts in Earth's climate. This extraordinary stability is not the result of chance, but of a combination of isolation, slow circulation, and the sheer scale of the deep ocean itself. The first reason these regions remain cold for such immense spans of time is their separation from the surface. Layers of water, thousands of meters thick, lie between the abyss and the atmosphere. Sunlight never reaches these depths, and surface winds cannot stir them. This physical isolation means that even major changes at the surface take a very long time to influence the deep ocean. Temperature signals weaken as they move downward, eventually fading almost completely. Circulation in the deep ocean is slow beyond ordinary intuition. Water that fills deep basins and trenches may take 1,000 years or more to complete a full circuit through the global ocean. During that time, it remains insulated from surface heat, changing temperature only through minimal mixing with surrounding water. Because all neighboring water is similarly cold, there is little opportunity for warming to occur. Deep basins act as thermal vaults. Their shape allows dense, cold water to settle and remain trapped, with limited pathways for escape. Once filled, these basins exchange water with the rest of the ocean only very slowly. The temperature inside becomes locked in, preserved by weak mixing and stable density layering. Over time, the basin's cold becomes self-sustaining, resistant to intrusion from warmer water above. Another factor contributing to long-term cold is the consistency of polar deep water formation. For much of Earth's recent geological history, cold water has continued to form near the poles and sink into the ocean interior. While the intensity of this process has varied, its persistence has ensured a steady supply of cold water to the deep ocean. This continual renewal reinforces low temperatures and prevents gradual warming. Geothermal heat, while constant, is too weak to overcome this effect. The energy released from Earth's interior is spread across the entire seafloor and absorbed by enormous volumes of water. Over millions of years, it may raise temperature by a fraction of a degree, but it cannot compete with the cooling influence of polar water formation and long-term circulation. Time itself plays a role. Because deep ocean processes are so slow, change unfolds gradually. Even if surface conditions shift dramatically, the deep ocean responds at a pace measured in centuries or millennia. By the time any warming signal arrives, it has been diluted, delayed, and smoothed into near invisibility. This delay allows deep ocean temperatures to remain effectively unchanged across multiple climate cycles. The stability of these cold regions makes the deep ocean one of Earth's most reliable climate archives. Layers of sediment on the seafloor record chemical signatures influenced by temperature, preserving a history of ancient oceans. The cold water above these sediments has remained consistent enough to protect this record from disruption, allowing scientists to reconstruct past climates with remarkable detail. For life, this long-term stability creates an environment of continuity. Species evolve slowly, adapting to conditions that remain constant across evolutionary timescales. Extinction pressures are lower than in rapidly changing environments, and ecosystems persist with little alteration. Temperature becomes a fixed background, shaping life gently rather than forcing constant adaptation. As we linger in these ancient cold waters, it becomes clear that the deep ocean operates on a timescale far removed from human experience. Its temperature does not respond to moments or years, but to epochs. The cold surrounding us has endured through continental drift, changing sea levels, and shifts in global climate, quietly maintaining its presence. In the final stage of our journey, we will step back and consider what this enduring cold means for the planet as a whole. The deep ocean's resistance to change plays a critical role in Earth's climate system, acting as a stabilizing force that connects past, present, and future. Why the deep ocean resists climate change? As we reach the final depths of our journey, the deep ocean reveals one of its most important characteristics: resistance. While the surface of the planet responds quickly to shifts in climate, the deep ocean changes with extraordinary reluctance. Its temperature does not follow the rapid warming or cooling experienced above. Instead, it acts as a vast, stabilizing force, absorbing change slowly and releasing it even more slowly over time. The primary reason the deep ocean resists climate change is its immense volume. More than 90% of the ocean's water lies below the thermocline, far removed from direct contact with the atmosphere. When excess heat enters the climate system, most of it is absorbed by the ocean, but the majority remains confined to the upper layers. Only a small fraction penetrates into the deep interior, and this transfer occurs gradually, stretched across centuries. Density stratification plays a critical role in this resistance. Warm water is lighter than cold water, and this difference in density creates a stable layering that limits vertical mixing. As surface temperatures rise, the contrast between warm surface water and cold deep water often increases, strengthening this barrier rather than weakening it. The result is a deep ocean that becomes even more isolated from surface warming. Time is another powerful factor. Climate change unfolds over decades, but deep ocean circulation operates on timescales of hundreds to thousands of years. Water entering the deep ocean today will not return to the surface for many human lifetimes. By the time surface warming signals reach the abyss, they have been delayed and diluted to such an extent that their impact is subtle and gradual. The origin of deep ocean water further reinforces this stability. Much of it forms in polar regions, where surface temperatures remain cold even in a warming world. As long as these regions continue to produce cold, dense water, the deep ocean will be replenished with near-freezing water. This process anchors deep temperatures to the coldest parts of the planet, rather than to global averages. Geothermal heat from below remains constant, unaffected by atmospheric change. Its steady but weak contribution does not amplify warming trends. Instead, it provides a faint background input that has been present for millions of years. Against this steady baseline, climate-driven changes appear small and slow at depth. The deep ocean's resistance does not mean it is immune to change. Over very long periods, shifts in surface climate can alter deep ocean temperature and circulation. However, these changes unfold so slowly that they resemble a gradual drift rather than a sudden shift. The deep ocean responds not to short-term trends, but to sustained changes maintained over centuries. This resistance has important consequences for Earth's climate system. By absorbing heat slowly, the deep ocean delays the full impact of surface warming. It acts as a thermal buffer, spreading change across long timescales and reducing extremes. At the same time, this delay means that once heat does enter the deep ocean, it will remain there for generations, influencing the planet long after surface conditions have stabilized. For life in the deep ocean, this stability provides continuity. Temperature remains one of the most predictable aspects of the environment, allowing ecosystems to persist even as surface habitats change. While shallow water species may face rapid shifts, deep sea life experiences change as a slow background process rather than an immediate challenge. As we pause in these depths, it becomes clear that the deep ocean is not passive. Its resistance to change actively shapes the planet's response to climate forces. By slowing, buffering, and storing thermal energy, it connects the present climate to the distant future, ensuring that change unfolds on a scale measured not in years, but in centuries. In the final chapter, we will bring our journey to a close by reflecting on the deep ocean as Earth's cold memory, a vast, silent archive that preserves temperature, history, and balance beneath the restless surface above. The deep ocean as Earth's cold memory. At the end of our descent, the ocean becomes almost perfectly still. Temperature no longer changes in any meaningful way. The cold surrounding us is not sharp or threatening, but calm and enduring. This is the deep ocean at its most fundamental level, a place where temperature is preserved, not actively shaped, and where the past lingers quietly beneath the present. The deep ocean holds the memory of Earth's climate in its cold. Every parcel of water here carries the thermal signature of the surface conditions under which it last contacted the atmosphere. In many cases, that moment occurred centuries ago, or even longer. Once water sinks into the abyss, it becomes isolated, its temperature locked in by layers of water above and the slow pace of circulation. The deep ocean does not forget quickly. This memory is not stored in a single location, but distributed throughout the global ocean. Cold water formed near the poles spreads slowly across the seafloor, filling basins and trenches with temperatures shaped by distant winters and long nights. As it moves, it mixes gently with other deep waters, blending past conditions into a smooth, global record. The result is a vast archive, written not in words, but in degrees. Unlike the surface ocean, which responds rapidly to change, the deep ocean responds only to persistence. Short-term warming or cooling leaves little trace at depth. Only changes sustained over centuries can alter the deep ocean's temperature in a noticeable way. This filtering effect ensures that the cold below reflects long-term trends rather than momentary fluctuations. The stability of this cold memory plays a crucial role in Earth's climate system. By absorbing and storing heat slowly, the deep ocean moderates the planet's response to external forces. It delays warming, softens cooling, and spreads change across long timescales. This buffering does not prevent change, but it shapes how change unfolds, transforming rapid shifts into gradual transitions. For scientists, the deep ocean's temperature is a window into the past. Measurements taken today can reveal information about climates that existed long before modern instruments. Sediments on the seafloor, influenced by the cold water above them, preserve chemical signals that tell stories of ancient oceans and atmospheres. The deep ocean serves as a quiet historian, recording events that unfolded long before human observation. For life, this cold memory provides continuity. Species adapted to the deep ocean evolve in an environment where temperature is one of the few constants. While the surface world changes rapidly, the deep ocean remains a place of persistence. Life here does not need to chase shifting conditions or adapt to sudden extremes. Instead, it unfolds slowly, in harmony with a stable thermal backdrop. As we reflect on the journey from the sunlit surface to the abyss, the contrast becomes clear. Above, temperature is fleeting and responsive. Below, it is steady and patient. The deep ocean exists in a different temporal frame, where centuries pass with little change, and cold becomes a defining feature of existence. This enduring cold is not empty or lifeless. It supports ecosystems, regulates climate, and connects the planet's present to its past. It reminds us that Earth operates on many timescales at once, some fast and visible, others slow and hidden. As our journey comes to an end, the deep ocean remains below, unchanged by our presence. Its temperature will continue to hover just above freezing, quietly storing the memory of Earth's climate long into the future. While the surface world rises and falls with the sun, the deep ocean waits, holding its cold, its history, and its balance in the darkness beneath.